Did we really discover life on an exoplanet just this week? No, we didn't quite do that, and here's why. New work has just been published about K218b, which is an exoplanet discovered in 2015 by the Kepler Space Telescope, and it happens to be one of the more habitable type of exoplanets we've discovered so far. It's very close to its star's habitable zone, and it may contain quite a few interesting organic compounds such as methane and carbon dioxide, but with it being so far away from us, for context it's about 30 times further away from us than Proxima Centauri is, it's quite hard to make very strong conclusions about anything on the planet. The team of Cambridge researchers used MIRI, which is the mid-infrared camera on JWST, to view K218b across and its transit across its host star. They argue, just like they did in their 2023 paper, that they have found a key biomarker called dimethyl sulfide, which on Earth is mostly produced by algae in the sea. So let's first look at how they came to this conclusion. We'll then look at one of the big critiques of their results, and then we'll just have a look about the limitations of certain biomarkers and sort of the whole biomarker argument just in general. When you collect data from JWST or pretty much any telescope, you need to make a lot of corrections and reductions before you can actually go through and use the data, and this actually takes up quite a big part of your data analysis because you're just dealing with a lot of stuff. This can include things like electromagnetic interference corrections, dark current reductions as well, that's quite a big one, linearity corrections, things like cosmic rays as well, you also may need to account for those. The list goes on. I think there's at least 10 individual things in this paper that they had to do to reduce the data. So it's quite a big part of data analysis. But interference and cosmic ray hits are things that we can get a baseline for because they're more to do with either your equipment or the general background, and so we have information on that and we can make pretty good reductions that won't actually detrimentally affect the data that much. In very robust data, once these corrections have been put in place, we should be able to begin to see some of the spectral lines. I know this is wildly different to exoplanets, but here is a spectra that I've had to do some data analysis on my own in the past, but it really highlights the point very clearly. This one's good because it's a very extreme scenario of once the appropriate corrections are made, you can very obviously see the spectral lines. So for example, you can see the H alpha and H beta in most of these, and this is due to Doppler broadening around the supermassive black hole in an AGN, so that creates the very broad lines. But in a couple of them you can also see the narrow lines, such as the oxygen 3 and the nitrogen 2, if I remember correctly which one it is. But yeah, in some of those you can also see that quite clearly and distinctly as well. These are very ideal conditions. They are rarely found in exoplanet data, and they are certainly not found with this exoplanet in particular. So in this paper, the team used two different ways to reduce the data, and you can see them differently in the orange and lilac. I've also got a picture of just one of these reduction pipelines, which is the brown data points with the error bars, and then they've also added some model fitting with the blue lines underneath that. What's important to note is that the brown data points and their error bars are the real data, and so this is kind of the only part of this plot that's actually really useful. And this is because corrections aren't perfect, and neither is JWST, although we don't really like to admit that. They all come with their own errors, of course, and so that sort of builds up and can have quite devastating consequences or effects to any models that you're going to fit if you're not cautious with the way that you reduce things. Now, on an absolute scale, these errors are small technically, but in the context of this, these are quite large errors that we've got over here, and they're exceptionally large on the right-hand side. And this is mainly just due to the observing capabilities of JWST. It's more focused on the shorter side of these wavelengths. On top of the brown data points and their error bars, they've also fit a light curve, which is the blue thick lines. And from that, they've been able to determine that the data fit their line curve better than a straight line fit, with a significance level of about 3.4 sigma. Significance in this context is more or less telling us, well, if there's no dimethyl sulfide present in this exoplanet, how likely are we able to recover these brown points, so this little bump that they're looking at, with a straight line fit? And 3 sigma is, I think it's like 0.7%, if I remember correctly. So 3.4 sigma is going to be less than that, probably around 0.1%. I'm just doing this off the top of my head, but the percentage is quite small, so it seems like it's very unlikely. Convincing? I'd say yes, given the sigma number and also the model fit. It looks quite intricate, but I'm kind of failing to see it from just the data points on their own. And what's really important here is that the model doesn't really mean anything. It's really the raw data that's important. A couple days after this paper was released, we had a counterpaper released which challenges the final statement, and it kind of challenges also these idea whether the model fits better to the data than the flat line, whether it's really a robust claim given the data and the errors that are present. And this is kind of important because their statement really hinges on how well their model is and how robust it is. One thing that I was kind of intrigued by is the fact that their model, so their sort of maximal model, includes more parameters than they have data points, which for me kind of is a telltale sign of overfitting. So the more complex your model is, the more you can get it to match your data points to fit exactly. But that's actually quite a bad thing. And if you have a lot of errors, so a very high uncertainty in your data, it can actually just make a model that just makes no sense. I'll show you a very simple example of this. Say I had like a very simple straight line relationship between two things, like spring constants, Hooke's law, spring constants, F equals kx. I think a lot of people who have done physics have done this during their high school, their A-levels, like really simple stuff. So the force, that's usually the weights that people put on a spring as it extends. It has a linear relationship between the extension, which is x, and the force, which is F here. And that relation, that gradient of the line, is the spring constant K. Now you're going to have quite a few different errors that arise when you try and, say, put different weights onto the spring and record those weights and the extension that you get. So when you go ahead to plot these data points, you're not going to get an exact perfect straight line. In fact, hopefully you will be able to at least recover a straight line relationship and be able to see that it should be that. But of course, even with the errors being quite small, you may have a little bit more of a squiggle or like a very wobbly straight line going on. And that's perfectly normal, that's kind of expected. In reality, you'll only need one parameter to fit this, and that's the spring constant, because you can see that it should be a straight line, and you just need one measurement or one estimation for the gradient, which is the spring constant K, and you should be able to get a pretty good fit there. But what if you just go wild and use like 100 free parameters and try and fit something super complex? Well, you're going to get a very squiggly line that will fit through your data points probably almost perfectly, but it's not really representing the actual underlying physics that's going on. And quite frankly, I think that's quite a poor approach to physics, as I'm sure you'll agree. Spectra are a really big tough beast when it comes to fitting them and sort of just doing analysis on them, mainly because there are so many different elements, molecules and compounds that may be present in a spectra to varying amounts and quantities. And so getting a model that can fit these fairly well without sort of creating false positives or like false negatives is quite difficult to do. It's so time consuming, which is why people spend most of their time actually focusing on that and all of the data reduction to be able to do this effortlessly and accurately. So it's a really slippery slope into overfitting, especially with the case of spectra. So there are a couple general guidelines that people tend to employ depending on the shape of the fits that they want to do, or sort of just the nature of the data, essentially, that will help you try not to overfit. So one example that is generally employed is that you tend not to use more parameters than you have data points. So for example, they had 29 data points in this, but they used 32 free parameters. I'd say that's quite overkill personally, and I think the authors of the counter paper also agree, or author, it was just one author, but yeah, my point still stands. There's quite a lot of overfitting that may be going on. So instead, in the counter paper, they fit much simpler curves and a straight line and try to have a look at which one may have a better fit, or if there's even much of a difference between the fits. And they found that actually, no, there isn't really much of a difference between the goodness of any of these fits. A flat line actually works perfectly well. And this kind of makes sense. If you overfit, the biggest consequence you have is that your model will go through the data points and match them very closely. So if you overfit with the intention of trying to get it to match closely, of course that fit is going to be much better than a flat line. You've kind of designed it that way. At the end of the day, I think the big conclusion that you and I should take home regarding both of these papers and all of the comments is that there isn't evidence for dimethyl sulfide, nor is there really any evidence against it. And this is because the errors on these mask any trend that we could really reasonably uncover with JWST. The noise is just simply too large, and we should try not to go into a research topic with the conclusion already sort of in our heads and then try and work backwards with the method. Now, I did say we'll end this with a brief chat on biomarkers. So dimethyl sulfide, or DMS, is an organic compound that includes sulfur, that contains sulfur. It's considered a biomarker because the way that it's produced on Earth is almost exclusively through plankton or algae in the sea, or it is also produced by cooking when you cook like root vegetables as well, which I thought was interesting. It's what gives it its smell. However, it is possible to actually detect DMS on things or objects that shouldn't really have life, such as comets and asteroids, which we have done in the past. And I do believe we've been able to produce it in conditions that are either abiotic or prebiotic in labs as well. So while it is a sign of life on Earth, and particularly sea life on Earth, I think one of the big problems we're having is that our understanding of how DMS is created is limited to how it's done on Earth, because that's all we really have. And so what it really shows to me is that our knowledge of how organosulfuric compounds, I think that's the word, are created just in general, because we have a heavy bias towards what's created on Earth and given earthly conditions, which most of the universe just doesn't have. I think this might be more of a personal opinion than more of a scientific one, or like a general consensus-y type thing. But I don't think there is really any single biomarker on its own that can really tell us, like, with full certainty that there is life on an exoplanet, regardless how good of your detection capabilities are of this certain thing. I mean, the only exception would be if you actually saw an alien with your own eyes or with the telescope. But yeah, apart from that, there isn't really any single smoking gun, really. But we were quite interested in K218b, mainly because it sort of lives within the habitable zone of its host star. So there was originally quite, reasonable interest in the star, in the exoplanet originally, but there are a lot of questions that actually need to be answered in order for us to actually get a full picture of the habitability of this certain exoplanet. I mean, for one, we need to have more insight into the atmosphere, whether or not it's sufficient, and what kind of compounds it's got, and whether or not it can actually produce the greenhouse effect, which should hopefully at least keep life stable. There's also, what's in the atmosphere we've already talked about, but is the magnetic field protected enough against the host star? It might not need a very strong magnetic field, given that the star's a little bit more on the dimmer and weaker side, but it still needs one. So at the end of the day, whether or not we've actually seen a particular biomarker doesn't actually throw away the question of whether there is life on a certain exoplanet or not. Particularly in this situation. For all we know, there could actually be life, and there could actually be DMS just within the atmosphere of K218b. It's just that the main problem here, and the main sort of issue that people are challenging right now, is the fact that we didn't detect it. Our error bars and our noise is just too much to actually make any conclusive conclusions, I guess, as to whether it is there or not. We just don't know. I think we all remember a similar story a couple years ago about phosphine on Venus, and once again, despite in this case the planet being right next to us at convenient times, we just couldn't detect any phosphine with reasonable confidence. And it's really tough, because a lot of these molecules are things that we would traditionally analyze and look at and experiment with, using a microscope or really small, like close hand samples, and yet we're trying really hard to do this with telescopes and really big distances as well. So it really throws a lot of difficulty into the mix. Thank you very much for sticking with me during my 4-week hiatus. I know that isn't a lot in terms of breaks, but I really did need it. I was quite busy with work. And yeah, just busy in general, so I had to put a hold onto YouTube for then, and also my website. But thank you very much for sticking around, and I hope you enjoyed this video. I will try and get back in with the flow of things, and I'll see you very soon.